G'day everyone. In this video I'm going to be going through a second method to evaluate an integral that I just did in a previous video. I'll have a link to it in this video description, which is the integral from 0 to infinity of sine of x over x. In the previous video we employed Feynman's trick and used differentiation by introducing a new function within the integrand and then differentiate. Here I'm going to be using Feynman's trick again, but instead of using differentiation, I'm going to use Laplace transforms, and this will allow us to be able to effectively get rid of having to need to introduce this element. Now they are very similar in the approaches. I just wanted to put them up just to give people an illustration of different approaches that one can take. Okay, so remember, this is the integral that we're working at. So the first thing we're going to do is we're going to introduce a new parameterization within the integral and create a new function I of t, which is the integral from 0 to infinity of sine of xt over x, where t in this case is a positive value. We see that the integral j, which is this integral here, is just this integral when it's evaluated at t is equal to 1. So if I put t is equal to 1 there, I've got sine of x over x, which is the integral that we want. Okay. Now, what we're going to do here is, as I said in the previous video, we used differentiation. Here I'm going to use a Laplace transform instead. So we're going to take the Laplace transform of I of t, which means we're taking the Laplace transform of this function here, which is the definition of I of t as we put it. Now, in order for us to be able to apply the Laplace transform to the integrand, we have to use a theorem known as Feynman's theorem. So just so you're aware of that, this integral is compliant with using Feynman's theorem, but in future, if you do want to apply this, that is something that you need to verify. As I sort of go through in the previous video, so I won't go into too much detail here, don't concern yourself with that sort of stuff too much at the beginning. If you're looking into this stuff for the first time, my recommendation is to just go out there and have fun and try as many different things as possible. Once you start picking up on a few of the different tricks out there, then you can start looking in the more rigorous elements of the analysis that is required. At the end of the day, if you apply a transformation within the integral, introduce a new function, apply a certain operator that doesn't comply with it, that means that the result that you obtain will be very easily detectable as being a non-realistic or you just won't be able to evaluate it in general. Okay, anyway, so as I said, we're taking the Laplace transform of this integral. Now, in order for us to take it of the integrand, as I said, we apply Feynman's theorem. Now here we're taking the Laplace transform with respect to t, so all of this stuff with respect to x can be brought out the front, so the 1 of x is out the front. And we're taking the Laplace transform of sine of xt, which is just equal to x over s squared plus x squared. If people would like to see a video showing how that actually comes about, by all means, please let me know within the comments and I will do a video to illustrate that. So here we've got the 1 over x times by x over s squared plus x squared. Now, one of the very nice things about this, if not the greatest thing about this, is that the x here cancels out with this x. And so we're just left with this integral from 0 to infinity, excuse me, of 1 over s squared plus x squared dx. This, again, is a this is a very easy integral to evaluate. It's similar to an integral that we had to evaluate in the other video. If anyone is unsure about how to integrate this, just let x equal s tan theta, and it comes out very, very simply. And we find that the integral is 1 over s times by arctan of x divided by s. So again, a very, very simple integral to evaluate. And again, this is the beauty of Feynman's trick when you combine it with different transformations, is that it takes something that is effectively impossible, or at least impossible by standard conventional known integration techniques and substitutions, and makes it a really easy task. So when we're evaluating these upper limits, there is just some things that we need to keep in mind. So arctan of infinity, positive infinity, is equal to pi over 2. Arctan is an odd function, which means arctan of negative infinity is equal to negative pi over 2. So the value of s here obviously will determine whether or not we've got pi over 2 or negative pi over 2. If it's positive, it's pi over 2. If it's negative pi over 2. Thankfully, we know with Laplace transforms that s here is actually a complex number, but that its magnitude is positive. So we know that x over s here is going to be a positive quantity as x approaches infinity, which means that our upper limit is equal to pi over 2. So we have 1 over s, which is just this component here, times by pi over 2, minus 1 over s. If we substitute x is equal to 0, arctan of 0 is equal to 0. So this component dies off, and we're just left with pi over 2s. So although we don't have the integral, which is what we want to have at the end, what we do know is that the Laplace transform of the integral is equal to this really simple term, pi over 2s. So in order to get I of t, if I've got the Laplace transform of a function and I want to get the function back, well, I take the inverse Laplace transform. So that's all we're doing here. We're taking the inverse Laplace transform, we're converting from s back to t of pi over 2s. We see that the pi over 2 is a constant, so we can just draw that out the front. And we've got the Laplace inverse of 1 over s, which is just equal to pi over 2 times by 1. So in case you were unaware, the Laplace transform of 1 is equal to 1 over s. So that's where this component has come from. Obviously, anything multiplied by 1 is just itself, so we have pi over 2. And as a consequence, we now know that I of t, which is equal to the integral from 0 to infinity of sine of xt over x dt, is equal to pi over 2. Now, what I love about this, amongst many other things, is that we've got no t dependency on the right-hand side. So regardless of the value of t here, t being greater than 0 in this case, you can actually have t being less than 0. You just end up drawing a negative out the front and it becomes the negative result of this. But for all t greater than 0, we get the same result. And so for me, I'm a big integral nerd. So that means that for me, I find this to be fascinating. This is brilliant, no matter what t is. As long as it's positive, actually. That's a condition that I did not see. I've made a mistake here. This should be t greater than 0, not t greater than or equal to 0. If t is, well, yes, no, because if t was to be equal to 0, then we would have sine of 0, which would be the integral from 0 to infinity of 0, which would be 0. And so it would not hold there. So please just make a note for yourself that there should be t greater than 0. And as I was saying, I'm going on, but for any value of t greater than 0, we have that it's equal to pi over 2. Now, we know in our specific case, we're looking for this integral here, which is sine of x over x. So that's when t is equal to 1. Well, I substitute t is equal to 1. There's no t on this side, so nothing changes. And we have that the integral, which we already knew, from 0 to infinity of sine of x over x is equal to pi over 2. So as I said, I will have the other video linked within this when I upload this video as well. This is just two different ways of evaluating the same integral. The reason why I provided two different methods is because I just want you to know that when it comes to Feynman's trick, you're not isolated to differentiation or Laplace transforms. You can think of anything, any sort of operator that you can apply to an integral and then evaluate it. Like, so generally you're applying it to the integrand. You can then evaluate that transformed integrand, and then you take the inverse operator in order to be able to resolve it. And so, I've been amazed at how I've been able to use, sometimes I couple differentiation with Laplace transforms, with Mellin transforms, with Fourier transforms. Sometimes I, instead of taking just the single derivative, I'll take multiple derivatives. I'll create systems of differential equations that come out of it. There's so many possibilities that come about from being able to employ Feynman's trick in order to take on really, really tricky and nasty definite integrals. So anyway, I'm getting overexcited, obviously. As with all of my videos, if you've liked this, please like it. If you would like to see more videos like this, please subscribe. If you have any suggestions or you have any requests on integrals, please either comment on this video here or send me a direct message. And if I'm able to do it and I have time to do it, I'll be more than happy to put a video up. But again, all feedback is welcome. Obviously, I make mistakes and I'm happy to correct them as I go along. I want you guys to be aware that when it comes to these sorts of things, I'm not perfect. I make mistakes. And so even when I think I've got it, completely perfect going into a video, I will make mistakes at times, and that's perfectly fine. It's about being able to process it as we go along, pick up on our mistakes and go, okay, not a problem. We're diligent as we go along, and we make sure that we pick up on any errors, which we've done. Okay, have a great day.